polynomials where n is bigger than 2 or bigger, mostly. 1, we get a line. We've done a lot with lines already. 2, we talked about in the last section. So polynomials have some nice characteristics that make them friendly functions. Polynomials are what we call continuous. That means no gaps, no jumps, no holes. So that's one thing that makes polynomials nice to work with. And another important property of polynomials is that they have no sharp turns. So the graphs are always a smooth curve. We don't get a sharp corner. And when you talk about this later in calculus, you'll call this property differentiable. Polynomials are differentiable. So that makes them behave nicely. So what we're interested in today is figuring out a little bit about how they behave based on their powers and these coefficients. And then later we're going to talk about how we can use these coefficients to figure out what the zeros are. First I want to draw some pictures. So I'm going to draw 4 different graphs. I'm going to draw 4 little sets of axes here. Because it turns out that in the big picture, a lot of polynomials behave very similarly to simpler polynomials. All right, so this first one is going to be y equals x squared. A nice easy parabola. How does that change if I had y equals negative x squared? It goes down. So we reflect over the x-axis. Do you remember what y equals x to the third looks like? Yeah, kind of an S shape, right? And it goes through the origin. Kind of looks like a tangent function, sort of. And then if we had y equals negative x to the third, it's going to go the other way. It's going to reflect, so it's going to look like that. Well, it turns out that any even-powered polynomial, if we just had x to the 4th, x to the 6th, x to the 8th, it's going to look more or less like this. And x to the 4th is going to flatten out a little more down at the bottom, but it's going to look more or less U-shaped. X to the 5th, x to the 7th, x to the 9th, going to look more or less like y equals x to the 3rd. They flatten out a little more through the origin, but they look very similar. And in just a second, we'll talk about this idea that this y equals x squared, on both sides, it just keeps going, gets bigger and bigger and bigger. Y goes up and up and up. Here it goes down, down, down. Down here and up here and down there. Other polynomials behave similarly. All right, so we're good with this, the visualization of these basic polynomials. All right, we're going to say that polynomials transform like we expect. This is just big big picture idea. Polynomials transform like we expect. So for example, we talked about this idea last time. So compared to y equals x squared, what does this function, what happens to this function? If we compare this, the graph of this function, to y equals x squared, what's different about this? Yeah? Yeah, this is right 3, up 5. If we had y equals x plus 9 cubed minus 3 and a minus, how is this, the graph of this thing, going to compare to y equals x to the third? It's going to, this negative is going to make it reflect over the x-axis. And then what else is going to happen to it? Down 3. Left 9. So this is what I mean by polynomials transform just like we expect. All the rules that we've talked about that you've talked about for transformations of functions in the past apply to polynomials. So they transform just like we expect. Yeah.
So if you have a reflection and a shift, and two, any other questions just asking like what are the transformations? Does it matter which order they go in?
It can. So to decide the order, follow your order of operations. All right. So that's all I'm going to say about transformations of polynomials. They transform just like we expect. The next thing that we need to talk about is called the leading coefficient test. The leading coefficient test is a way that we can tell what happens to our function eventually. So what we're interested in is f of x equals a sub n x to the n plus dot dot dot. All we care about is the term with the highest power of x. And the leading coefficient test tells us what happens as x gets really big. So it gets large, so it goes towards positive infinity, or small, towards negative infinity. The other way that you might be asked this question is, what is the right and left-hand behavior?
So what's that first thing in the bottom?
And the last, another way is, the way that I think about this is, what happens eventually? So what we're asking when we're talking about the leading coefficient test or the right and left-hand behavior is, what happens as x gets really large, as we go way, 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 way over this direction, or as x gets really small, way, 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 way over this direction? What happens to our function? Well, the leading coefficient tells us everything we need to know. So I'm going to say n is even. And the other condition is when n is odd. And we have our leading coefficient greater than 0 and a sub n less than 0. So we're making a little chart here. So as x gets really big, if n is even the highest power in x, 2, 4, 6, 8, and our leading coefficient is positive. Eventually, our function behaves like y equals x squared, and it goes up on both sides. If n is even and the leading coefficient is negative, eventually it behaves like y equals negative x squared, and it goes down on both sides. It can do all kinds of stuff in between, but the leading coefficient test tells us that eventually this is going to happen. Eventually, this is going to happen. If n is odd and our leading coefficient is positive, eventually our function acts like y equals x to the third. So it's down on this side and up on that side. It can do all kinds of crazy stuff in between, but eventually it's going to do this. So I don't care about this now for the leading coefficient test. And if n is odd and the leading coefficient is negative, eventually it's going to behave like y equals negative x squared. And it's going to do this. X cubed, sorry. You're right. So when the question asked you about the right and left-hand behavior, or what happens when x gets really large or really small, you look at the leading coefficient, highest power of x, and you draw these little arrows. You don't have to do anything else. So your problems 29 through 36 odd in the homework, they all have to do with this. You're just drawing little arrows. So for example, the right and left-hand behavior of minus x to the fourth plus 7x to the third minus 14x minus 9. All right, so the leading coefficient. What's our highest power of x? X to the fourth. This is the only one we care about. Even exponent, negative sign. So what does that tell us our right and left-hand behavior is? Down and down. This function might go do all kinds of crazy things in between, but eventually our graph, if we graph this thing, it's going to go down on this side and down on that side. How about, I'm just going to write f of x equals, just to make myself feel better. All right, so we want the right and left-hand behavior of this thing. Our leading coefficient, is that the first one?
No, it's the second one.
The second one?
Actually, no, it's like the second to last.
Second to last, it's the highest power of x. All we care about is this one. Odd exponent, positive coefficient. So what does this do? Down here and up here. It behaves eventually like y equals x to the third. And that's, it can do all kinds of crazy things in between, but eventually it's going to do this. So what we're going to do is use the leading coefficient test to help us sketch a graph of these things. Well, let's look at a couple of other tools that we're going to use to help us sketch graphs. We'll use these tools for other things, but they'll also help us sketch graphs. Zeros of polynomials. Zeros of polynomials is really the key. That's the main idea of chapter 2, is finding zeros of polynomials. We'll do some other things, but zeros of polynomials is really the key idea. We're going to say f is a polynomial. And a is a real number. I'm going to list 4 things. All 4 of these mean the same thing. One, x equals a is a 0 of f of x. So 0 means we plug in a for x and we get out 0. So that's one of the things, it's one of the 4 things that are all going to mean the same thing. The second thing that means the same thing is this. X equals a is a solution of the equation f of x equals 0. These 2 things mean the same thing. Finding a 0 of a polynomial is the same as solving the equation f of x equals 0. The third thing that means the same as these 2 things. X minus a is a factor of f of x. And a reminder about what we mean by a factor. That means we can write f of x equals x minus a times, we get a bunch of parentheses, dot, dot, dot. But one of those sets of parentheses is going to be x minus a. Because when I plug in x equals a here, this is 0 times all this other stuff. I get 0. I get 0. The fourth thing that means the same thing as these other 3 is that the point a0, and again this is a point, is an intercept, X-intercept. Of the graph of f of x. Well, this says we plug in a and we get out y equals 0. This says we plug in a and we get out 0. This says we plug in a and we get 0. This says we factor like this, but we plug in a and we get 0. All 4 of these things mean the same thing. All 4 of these things are different ways you're going to be asked the same question in chapter 2. And we're going to go about solving these 4 different types of problems that are really one problem the exact same way. And we'll use these things to help us sketch graphs of functions along with the leading coefficient test. I'm going to say one other thing here. A polynomial with degree n. So our highest power on x is n, has at most n real zeros and n minus 1 maximums and minimums. And the way we can, the other way we can think of this is turns. So it turns around at a maximum or a minimum. So if our degree is n, it has at most n minus 1 turns. So a parabola, how many turns does a parabola have? 1. Or a second degree or third degree polynomial could have 2 terms. So that's what we're saying. All right, so let's look at an example of applying this, and that example is going to lead us into one other interesting thing about polynomials. we want to find the x-intercepts. We want to find the x-intercepts of this function. So we think, well, how do we find the x-intercepts? We need x-intercept is where the function equals 0. Well, that's also the same as where we get a solution of x cubed minus x squared minus x plus 1 equals 0. But that's also the same as saying that we want to find the factors of x cubed minus x squared minus x plus 1. How do we find the factors of this thing? We factor. Factoring is the same as solving. Factoring is the same as finding zeros. Factoring is the same as finding x-intercepts. They give us the same information. So we're going to factor this. Factoring is going to be a huge thing in Chapter 2. That's one of our big things that we do in Chapter 2 is factor all kinds of stuff. So someone said it. How do we factor this? Factor by grouping. 4 terms suggest factor by grouping. So I'm going to group these 2 terms, and I'm going to group these 2 terms. So this first, x squared times x minus 1. And here I'm going to factor out a minus 1. So I get an x minus 1 there as well. So this is x squared minus 1 times x minus 1. Can I factor x squared minus 1?
You do an x. No. That's y.
How about x plus 1, x minus 1 times x minus 1? And then I could write this as x plus 1 times x minus 1 squared. X minus 1 times x minus 1 is x minus 1 squared. This gives us some information, we'll talk about this in just a second, about the graph of this thing. So where are the x-intercepts?
-1, 1.
And x-intercepts are points. So the x-intercepts are at -1, comma, what's y equal at the x-intercept? 0 and 1, 0. Those are my x-intercepts. And I got the x-intercepts by factoring. X equals -1 and x equals +1 are the zeros of that function. X equals -1 and x equals +1 are the solutions of this equals 0. So all those things mean the same thing. And the fact that this x minus 1 times x minus 1, we have 2 of those, that tells us something about the graph of this function. So that's the next thing we need to talk about. All right, questions on this example? All right, so the next topic is multiplicities of routes. All right. A factor, x minus a to the k, for k bigger than 1. So that means we have x minus 1 squared like we did in the last one, x minus 5 to the 5th, x plus 7 to the 18th. We call it a gives a repeated 0. X equals a. And the reason we say it's repeated is because we can write this x minus a times x minus a times x minus a times x minus a. So we get those things repeated. So we get a repeated 0, and we say that it has multiplicity k. So I'm just going to pop back here really quickly. Here, I have a repeated 0 of x equals 1, and that 0 has a multiplicity of 2, because we get 2 of them. 1 and 1 here. If k is even, the graph touches the x-axis at x equals a. Sometimes people call it bouncing, but it touches, it's tangent to the x-axis. So it touches the x-axis. If k is odd, the graph goes through. At x equals a. So it's going to cross the x-axis at that particular point. So the multiplicity tells us what the function is going to do at that particular point on the x-axis. So y equals x squared, our zeros, our solutions of that, zeros of the function are x equals 0. Well, we could write x squared as x times x. So that 0 has a multiplicity 2. So right at x equals 0, our parabola touches the x-axis. And it can't come back through the x-axis because that's the only 0 of that function. So we're going to use our left and right hand behavior, our zeros, and our multiplicities to sketch graphs of functions. So let's take an example of that. Questions on this? So we want to sketch a graph of f of x equals x cubed minus 2x squared. All right. So the first thing we'll do is look at our right and left hand behavior. So our leading coefficient, highest power on x, x to the third, leading coefficient is positive. So our right and left hand behavior is going to be this. So eventually, our graph is going to go down on the left and up on the right. It's going to do some things in between, and we'll find out what those are. Well, let's find the zeros. How do we find the zeros of this? Factor. F of x equals x squared times x minus 2. So my zeros are x equals 0, and we have a multiplicity of 2. So it's going to touch the axis. Here we have an x equals 2, has a multiplicity of 1, so it's going to go through. So here's my sketch. Here's my x equals 0. Here's my x equals 2. There aren't any other zeros, so I know that on the right, after it goes through the x-axis here, it's going to do that. And I know that on the left, it doesn't go back through the x-axis. It's going to do this. But since this has a multiplicity of 2, here at x equals 0, it does this. And it turns around. Well, it has to turn around here somewhere and go back up. Doesn't go through the x-axis anymore here. Well, how do we figure out if it's way, way, way down here or just barely dips below the x-axis? Plug in x equals 1. F of 1 equals 1 cubed minus 2 times 1 squared, which is negative 1. So it's gonna, there'll be a point down there, and my graph does something like that. So that's a rough sketch of that graph. If we plugged in x equals 1 and we got negative 1,000, then the graph would go way down here before it turned around and came back up. Third degree polynomial has 2 terms. And it has 3 real zeros, because x equals 0 counts as 2 of them, because it has multiplicity 2. So in general, when you're sketching a graph, use your right and left hand behavior. Find your zeros, plug in some points between your zeros, plug in some values of x to figure out how steep your graph goes up and down between there. All right, questions?
It's only like multiple choice. It's on Thursday.
Skip 46 in that section. All right, there we go.